You've trained a machine learning model. Now you want to make use of it in your applications and website. You want to use machine learning to achieve what human cannot possibly achieve, which is highly accurate prediction and automation. But it begs questions. How do you host your ML models in a way that your customers has the best experience on your product powered by ML models? How do you achieve optimal latency so that thousands of your customers using it all together won't feel it? How do you at the same time maintain appropriate budgets? Goldman Sachs Global Investment Research Group runs a public-facing research portal that publishes 350 valuable reports and models every day. The portal has 1 million clients globally. It's powered by ML model hosted on Amazon SageMaker. What is it that they do to achieve it with just a team of 4 data scientists in 4 months? Welcome to this session, Achieve High Performance and Cost-Effective Model Deployment, featuring Goldman Sachs. My name is Michael Xie, and Senior AI ML Specialist Solution Architect from AWS. Joining us today is Pravalika Ittori, a machine learning engineer from Goldman Sachs. We'll talk about the model deployment options in Amazon SageMaker in this session, and then we'll show you how to optimize your model deployment. We will summarize with a decision tree to help you make better decisions, and we will learn how Goldman Sachs peels the onion and find out the best architecture pattern to achieve milliseconds latency inference for their research content recommendation engine behind the website. So you may be asking, why optimizing model deployment? ML inference is what your customer experience from your service and products. In fact, ML inference is your product. You may have found that the ML spending is largely in ML inference, in the persistent compute instances, and cost in managing the infrastructure. To maximize your ML investment, choosing an appropriate hosting methods and right-sizing the infrastructure are needed to scale model deployments. These are the top 5 dimensions from business requirements to engineering when deploying models. The first pillar is SLA, Service Level Agreement. How quickly do you promise your customers about your service and ML inference? The second pillar is cost. What is the budget for your model deployment for your organization, and how do you control it? The third pillar is compute resource, more into the engineering side of things. What type of instances should you use? How to manage the infrastructure and make sure they're efficiently utilized. Fourth pillar, the data. What is the nature of your data and how are they collected? And is there any potential data drift during inference? And how to detect them? The fifth pillar, models. How did you train your models? What is the size of your model? And what is the runtime behind the models? How many models do you have for one use case? All these factors play a role in determining optimal hosting options. Amazon SageMaker, as a fully managed ML service, provides what you need in model deployment. It is easy to deploy ML models in the cloud. With simple API calls, you can deploy models trained in and outside of Amazon SageMaker, pre-trained models from SageMaker Jumpstart, or even Hugging Face model zoos. It also supports online and offline scoring. Online scoring is designed for low latency, real-time inference at scale. Offline scoring is designed to operate at high throughput for large dataset. SageMaker is also fully managed. Being fully managed, Amazon SageMaker takes care of the web serving framework, infrastructure setup, and load balancing. Example SDK calls for online and offline inference are shown below. Just 2 lines of code. It's very simple. So deploying models are easy. What's a big deal? Ever thought about questions like, should I use online or offline scoring? How many instances should I use? And what instance type should I use? How do I guarantee a single-digit millisecond response under a certain load? Devil lies in the detail. Let's take an in-depth look at the model deployment options in Amazon SageMaker and how they work. First, SageMaker Batch Transform is an offline, batch, asynchronous feature that makes ML inference on the bulk of data against your model. All you need to do is to bring in your model and inference script. Designed to work with large dataset, there is an agent in SageMaker Batch Transform that performs a mini batching to provide high throughput. As a fully managed feature, the instance provisioning and deprovisioning is automatically done, and you only pay for the compute instances for how long the process takes. It is suitable for periodic bulk data inference by schedule or by trigger, and use cases where you want population statistics or do not need real-time response. For example, in research studies or demand forecasting. SageMaker real-time inference creates a long-running microservice with HTTPS endpoints and RESTful API for invocation. Being fully managed, SageMaker sets up the compute instance, serving framework, HTTPS endpoints, and load balancing for you. You only need to bring in the models and inference script. It can provide the instance response in milliseconds up to 60 seconds for a payload up to 6 megabytes. And thanks to HTTPS endpoint, your models is accessible from an external application globally. As your business grows and customer base grows, you can also use manage all scaling to scale out the instance fleet elastically to handle the traffic. Real-time inference is suitable for a wide array of use cases such as content recommendation and fraud detection. If we decouple the simple one line of code shown previously, model deployment is a three-step process. First, create a model from a container and your model.tartgz, which is the model artifact. Second, create an endpoint configuration where you specify the instance types and instance count. Third, you create an endpoint with a configuration. Then you invoke the endpoint with the payload using SageMaker Runtime Client. Real-time inference is great, but in some use cases, typically in NLP, natural language processing, or computer vision, CV, where either the data size is large, for example, high-res images or videos, or inference processing takes longer time, you will not be able to use real-time endpoints. Asynchronous inference is a new SageMaker model deployment option that was released in August 2021. It is ideal for models that take longer than 60 seconds up to 15 minutes and payload size larger than 6 megabytes up to 1 gigabyte to process and return results. This would not have been possible with the real-time inference option. The auto-scaling for asynchronous inference even supports scaling down to 0 instances so that you don't have to pay for the endpoint when there's no request. Inside asynchronous inference, what's enabling the longer resource demanding processing is an internal queuing system that handles the request in the queue. Instead of sending the data in payload through the REST interface, you upload the data to S3 and invoke the endpoint with the S3 object URI. Asynchronous endpoint would take the object from S3, make inference, and then save the results back to S3 bucket. Optionally, you can provide Amazon SNS, simple notification system, service topics for the endpoint to notify successful and failed attempts. To set up, you will create a model as usual, create an endpoint configuration with additional setting for asynchronous inference such as output location, SNS topics, and concurrency per instance. Then you will invoke using a new API, invoke endpoint async to specify the input location. As your ML portfolio grows, you need to start thinking about cost for hosting these models. For example, you have a use case where you are building a models for for each geo area that your business is growing into. You are hosting the new models every 6 months and paying instances for 24/7, even for the ones that are less frequently used. There are two more SageMaker model deployment options: multi-model and multi-container endpoints for cost-saving opportunities. They are designed to work with multiple models behind one endpoint. So instead of hosting 4 endpoints for 4 models, you can host 4 models in one endpoint with these two options. SageMaker multi-model endpoint addresses such situation. Multi-model endpoints can host multiple models in one container with direct invocation to a target model. It improves resource utilization. That is, less frequently used models can now share the instance with the more frequently used models. You only need to put all the data in a dedicated S3 location, and multi-model endpoint automatically and dynamically loads the models from S3 into memory and unload them when not in use. However, if you have models that have significant higher transaction per second or latency requirements, we recommend hosting them on a dedicated endpoint. Multi-model endpoints are well suited for scenarios that can tolerate occasional cold start related latency penalties that occur when invoking infrequently used models. To set up, you specify your multi-model supported container in a multi-model mode and provide an S3 location for all models that you need to host. Then you create a model and create an endpoint configuration and endpoints as regular endpoints. When invoking the endpoints, you can specifically target the request to a model with target model argument. Multi-container endpoint, on the other hand, can host up to 15 distinct containers, meaning you can have diverse ML frameworks and functionalities across containers and models. You can host 15 models for direct invocation or for serial invocation. Serial invocation, as known as inference pipeline, is suitable for combining pre-processing and model inference in one endpoint. And because of all containers are running at the same time, there's no cold start issue. To set up, you create individual containers, put them in the list when creating a model, and specifying the models to be direct or serial. Create an endpoint configuration and endpoint as usual. At invocation time, you can specify the target with target container host name if using the direct mode. Those are the deployment options in Amazon SageMaker. Now, for endpoint performance, measured by latency and throughput, one of the major factors is the instance of choice. Using SageMaker, you get a wide range of instance options to choose from when deploying models. They fall into 3 categories. Number 1, the CPU instances. They are low cost, low latency, flexible for diverse ML frameworks, though the throughput is lower compared to the other 2. The GPU instance are for newer network models that can benefit from GPU devices and have higher throughputs, much lower latency. And last one, AWS Infinite instances with custom inferential chips are designed for deep learning models inference. They have 2.3 times higher throughputs and ultra low latency. They are 70% lower cost per inference compared to GPU instances. However, you need to check for framework supports and custom operator support for your models. With all the options discussed, Still, the question remains, how do I even know what instance and endpoint configuration is optimal? Load testing is our friend. Load testing is a practice to generate artificial traffic to an endpoint and see how the endpoint hold up and its performance characteristics as a function of traffic size, instance type, and instance count. In the context of inference endpoint in SageMaker, we can illustrate the process in this diagram. A SageMaker endpoint consists of HTTPS endpoint, a load balancer, and ML instances. You can attach an auto-scaling policy that will scale out and in based on the certain metrics to a SageMaker endpoint. The load balancing in the SageMaker endpoint distributes the traffic to instances, and SageMaker emits the invocation and instance metric directly to Amazon CloudWatch. So by doing load testing, you can observe the response of your endpoint configuration in Amazon CloudWatch. Later in the demo, we'll dive deeper into load testing and how to analyze results in Amazon CloudWatch to help you find the best deployment configuration. Okay, now we get all the options out of the way and let's see what a decision process will look like with all these options in your arsenal and when it comes to optimizing model deployment. First, we gotta ask ourselves, is there a live traffic that you need to host your model for? If the answer is simply no, then the most cost-effective way is to use SageMaker Batch Transform on your data for such data. And if there are live traffics, then we have to ask ourselves whether the payload is under 6 megabytes or over 6 megabytes. And also the runtime, the processing time of the model inference, does it take more than 60 seconds or less than 60 seconds? We could use Amazon SageMaker asynchronous inference for a large payload and longer inference. And if the answer is no, and then we can consider, okay, so do we have multiple models or containers to host? And for cost-effective options, we can choose different types. So if you have only one models, we can use the regular SageMaker endpoints. And if there are multiple models and containers, and we need to see if they're all single framework, or they come from multiple different ML frameworks or different functionalities. And for single framework models in one container, we could use multi-model endpoints. And if there are multiple containers with diverse frameworks, and we could use SageMaker multi-container endpoint. And this is also suitable for inference pipeline use case. And for these real-time hosting and asynchronous hosting options, it's best practice to conduct load testing to right-size your instance type and instance size. Then we need to consider whether there is a fluctuation in traffic. If there is, then we need to apply auto-scaling policy to your endpoints in order to handle the traffic. Besides optimizing for model performance and cost, equally important, if not more important, is to optimize your model accuracy after it goes live. SageMaker Model Monitor enables you to monitor drift in 4 modes: model quality drift, data drift, feature importance drift, and data bias. In the first mode, SageMaker Model Monitor uses data capture from invocation in S3 and ground truth provided by you in S3, and sets up processing job in the schedule and computes the model accuracy during the interval. And then you can visualize the model accuracy over time in SageMaker Studio UI easily, and sets up alert in Amazon CloudWatch when model accuracy dips. What if you don't get ground truth in time to compute the accuracy? You could use the next mode. SageMaker Model Monitor can also compute one-time descriptive statistics and statistical distribution on the baseline training data, and uses those statistical characteristics to detect data drift and use data drift as a proxy to tell if the model is still appropriate for the live data. Model Monitor in this mode also detects data type inconsistency and missingness. Last but not least, SageMaker Model Monitor can compute the feature importance changes and data bias in the incoming data with the help of SageMaker Clarify. You can tell if it's time for model retraining to maintain the model accuracy by tracking how model is making decisions. With the next iteration of your awesome model, we need to think about how to verify the performance against the latest and last working model. Conducting A/B testing is made easy with Amazon SageMaker. You don't have to take down the current endpoint. You can attach a new model as an endpoint, as a production variant behind the same endpoint and control the flow of the traffic with SageMaker endpoint. As shown in the code snippet, after the new model is hosted, we can set the desired weight to the models from 100% current models into 90% to the current model and 10% to new models, and observe and analyze how the new model behaves, and shift the traffic for further analysis if need be. Until the new model is verified, you can then take the full traffic completely to the new model. You can also set up data capture and directly invoke full dataset against each model for paired testings. SageMaker model deployment is also integrated with SageMaker's MLOps capabilities. I'd like to recommend a related session about CI/CD and MLOps for your ML models. Please visit the session AIM 320 Implementing MLOps Practice with Amazon SageMaker. Now we're getting our hands dirty with the demo. Imagine you have a use case where you are creating numerous models by geo-region in order to have a more localized understanding and prediction of your customers' behavior. While you can host each model in an endpoint, you will soon dealing with management overhead and start burning budgets. In this demo, we show you how you can optimize your deployment for cost and performance. We will host more than 50 ML models based on one single ML framework in a SageMaker multi-model endpoint to predict customer churn based on account usage. The models are trained using the synthetic telecommunication customer churn dataset and SageMaker's built-in XGBoost algorithm. We will host 2 multi-model endpoints on 2 different instance types with different compute capacity, and compare the performance with a load test using Locust, a distributed load testing framework in Python, in order to find out an optimal hosting configuration. We will then analyze the load testing results in Amazon CloudWatch as shown in this figure. First off, we load a customer churn dataset from the synthetic telecommunication use case. The dataset contains customers' account usage, locality by states, and churn status, which is our target variable. We perform minimally required data processing in order to use SageMaker's built-in XGBoost algorithm. We hold out 10% of the data stratified by state for load testing purposes and save the data into S3. We perform model training for customers by states with the SageMaker XGBoost algorithm. We have a launch training jobs utility function for convenience to submit the training jobs in a for loop. In the loop, we further split the state-wise data into train and validation set for training and submit the jobs using launch training job function. These training jobs are tracked by SageMaker experiments. They take about 10 minutes to finish. For demo purposes, I am loading state-wise
training estimators from past experiment into a dictionary, thanks to SageMaker experiments tracking the jobs. So we have 51 estimators in this dictionary. We are ready to deploy SageMaker multi-model endpoints. As described earlier, multi-model endpoints dynamically loads models from the S3 location. We need to designate a location and copy the models from their original output location to this location. Note that this action can be done at any time, before or after the endpoint is created, making multi-model endpoints a flexible tool to serve model at scale. We create our first endpoint with the MLC5X large instance with 4 CPU and 8 GB of RAM. To create a multi-model endpoint, we specify the container image for hosting. For XGBoost, this refers to the same image used for training. Model data URL for S3 location for the model artifacts, and set the mode to multi-model mode. Then we create an endpoint configuration specifying the instance types and configuration. The last step is to create an endpoint with such configuration. We follow the same steps to create another endpoint with MLC5 large instance that has double the compute resource. We reuse the model created previously, so the create model step is skipped. Then we create an endpoint configuration and endpoint, similarly just with a different instance and name. We can wait for the endpoints to spin up. Meanwhile, we can move to set up the load testing in AWS Cloud9. AWS Cloud9 is a cloud-based IDE that lets us write, run, and view applications in the browser. We prepare a load testing experiment with Locust. We can generate artificial online users to perform actions. Because the testing would take about 2.5 minutes to ramp up and show something meaningful in the dashboard, let's kick off the testing first, and I will explain what is happening in the meantime. In our experiment, each online user will randomly load the data point from the testing set we held out and request against the state corresponding model in the multi-model endpoints for a prediction. This is designed in the locustfile.py, which we used in the shell script. We use invoke endpoint API from both 3 SageMaker runtime client to make invocation. The response status of the invocation is captured by Locust for summary. We specify the target model by target model argument. And the target model is determined by state column in each data point. And in the shell script we launched previously, it starts a 2-worker distributed load testing job that creates 300 online users with a spawn rate of 5 new users per second, hitting the respective endpoint for 15 minutes. So in 60 seconds in, we should have 300 users hitting each endpoint. As we can see in Locust UI for the 2 jobs, the online users are being spawned. There are also other metrics captured in the UI for analysis purposes. We can look at the dashboard for another load testing job. Similarly, we can track the status of the load testing. We can observe the rate of invocation here for this job at 240 requests per second and 50 for another job. Let's go to Amazon CloudWatch to analyze the load testing with the dashboard we prepared. SageMaker endpoints, including multi-model endpoints, integrates with Amazon CloudWatch and emits metrics that capture the health and the statistics of an endpoint to Amazon CloudWatch at a 1-minute frequency. We can visualize the metrics here directly, like in this dashboard. We can also use other tools to visualize the result. This dashboard displays the key metrics and charts from the 2 multi-model endpoints on the load. The top half is the larger instance, C5 2x large, and lower half is C5 x large. And we highlight the latest rolling average as a banner on top and the metrics below. The main categories of metrics that display here are invocation metrics, including errors, latency metrics, and also instance metrics, including the CPU and memory load. We can quickly observe a couple of things happening from 300 simultaneous artificial users hitting each endpoint. There are close to 10 times more invocation allowed on the larger instance, and there are about 1/10 of latency on the larger instance. All 51 models are loaded into memory in the larger instance, while only 35 models are loaded in the small instance C5X large as hot models for invocation. As a consequence, there is a constant loading and unloading of models in and out of the memory, which takes close to 800 milliseconds on the smaller instance. There is also a whopping 3.5 seconds model loading wait time, which indicates how much time in average an invocation has to wait multi-model endpoints to load a model for inference. CPU and RAM utilization are different too. The smaller instance constantly going beyond 100% of CPU utilization attributed to a longer latency, and there is a much higher RAM utilization, preventing multi-model endpoints to load more models into memory. Comparing the performance and characteristics of the two endpoints, we can conclude that the MLC5 2x large gives a better stable throughput and lower latency when there is a maximum 300 simultaneous user calling endpoints compared to using a MLC5X large instance. Using one single MLC5 2x large instance allows us to serve all 51 models without constant loading and unloading and maintain a desired single-digit millisecond latency. We don't need to host 51 endpoints / instance, hence there's a significant cost saving. In your unique use case, you may have different latency requirement, different load pattern and expectation. You are welcome to perform more tests using other instances, adding more load, and adding auto-scaling policy to conduct the test according to a unique use case.
Now with the demo, we learned how we can optimize model deployment. And now it's our privilege to have Pravalika to join us and talk about Goldman Sachs' journey on Amazon SageMaker.
Thanks, Michael. Thank you for having me. My name is Pravalika Ituri, and I'm a machine learning engineer at Goldman Sachs. Today, I'm going to talk about how Global Investment Research Division of Goldman Sachs uses SageMaker. Before I get into the machine learning side of things, let me give you an overview of Goldman Sachs and Investment Research Division. Goldman Sachs is an investment banking, securities, and investment management firm that provides a wide range of financial services to a diversified client base that includes corporations, financial institutions, governments, and individuals. Global Investment Research, in short GIR, is a division of Goldman Sachs which provides original fundamental insights for clients in equity, fixed income, currency, and commodities markets. We have around 1,000 people across the world covering around 3,000 securities over 45 economies and every major market. Our research analysts publish content on a varied range of topics and also host conferences and webcasts to connect our clients with subject experts. The way we reach our clients is through a variety of distribution channels, our primary one being a research portal, publishing.gs.com. We also have a mobile app, GS Now, available in Android and iOS. We also serve our content via Marquee, which is another product of Goldman Sachs. Every day, GIR publishes around 350 reports, blogs, and financial models. We have a client base of over 1 million across the world. It is difficult for our clients to consume all the published information on our platforms. Due to the high volume of traffic and high production frequency, we needed a recommendation engine to serve relevant content to our clients. So, we identified 3 different recommendation use cases on our content. First one being report recommendations. So, we built a personalized recommendation engine to recommend the most relevant content to the clients so that they can read the reports that they might have missed reading due to the high volume of publication. On the screenshot here, you can see that the component saying reports you may have missed is how we serve the personalized report recommendations. For this purpose, we're using an XGBoost model. The second use case is follow recommendations. In GIR, we have the concept of tags. Every piece of content is tagged with appropriate topics, and users can follow these tags to receive notifications when a related document is published. We built a personalized follow recommendation engine so that the clients can easily follow the tags that they are interested in. We use a collaborative filtering model for this purpose. So the recommended follows component in the orange box that you see corresponds to the follow recommendations, and the users can easily click on the follow button to follow a tag that they're interested in. The third use case is the related reading recommendations. When a client is reading a report, we recommend them related content to the current document that they might be interested in reading further. So for this purpose, we're using universal sentence encoder embeddings, and you can see the component in the screenshot here. All these three models are currently running in production, and the end product is the one that you're seeing on the slide. Now, let me get into the implementation details. Before starting, we had a few requirements to build these models. We needed a cloud-native solution. Around 2 years ago, our client-facing portal publishing.gs.com migrated from GS infrastructure to AWS. We even had a recommendation engine on-premise at that time, which got demised due to this AWS migration and few other reasons. So we wanted our new ML workflow to be cloud-native to align with our other services. We needed fast model predictions. So since our recommendations are external client facing, we needed low latency predictions for a seamless client experience. Quick to deploy models. We needed a setup for efficient model deployment so that our data scientists can spend more time in building the models and less time on infrastructure. Lastly, we needed highly available and scalable inference due to the high volume of our traffic. Based on all our requirements, SageMaker was a suitable solution for us. Once we did a proof of concept of SageMaker, we started to build an end-to-end model-agnostic architecture for training and deployment of our models. So starting with the architecture, we have two data sources in our system, Snowflake and Adobe Analytics. Snowflake is our data warehouse, and all our client tracking data gets streamed real-time to Adobe Analytics. So we have two data fetching lambdas, which fetch data from these sources and upload to an S3 bucket. And we use the AWS step functions to process different steps in our machine learning workflow. We have another lambda, which we call as workflow lambda, which orchestrates this flow. We use step functions data science SDK for this purpose. So we pass the location of training and serving image to this lambda, and upon the start of execution, it first starts a train step, which runs the training script on the data in the data bucket and creates a SageMaker training job. Upon the completion of this training job, the model artifacts are uploaded to a different S3 bucket. Then, the next step accesses these model artifacts and creates a SageMaker model resource. The third step is the SageMaker endpoint config step, which uses the provided configuration values on the lambda and creates an endpoint config resource. Then we have the create or update endpoint steps, which update the endpoint with the new model information, or if the endpoint doesn't exist yet and it's the first time the training job is running, it creates an endpoint. We use CloudWatch triggers to automatically invoke all these lambdas at required frequencies. The trigger for the workflow lambda helps us automate the retraining and desired frequency based on the use case. By the end of this workflow, we have all the SageMaker resources required from training to inference. In the next part of this talk, I'm going to focus mainly on the deployment and the inference side of things. SageMaker provides out-of-the-box algorithm and container options, but also has the option of custom container. We took the custom container route and we used an image created by the core ML team of Goldman Sachs, which has all the required libraries like TensorFlow, PyTorch, and Scikit-learn. We also use our own training and inference code. For hosting the endpoint, we need to choose a suitable instance type. SageMaker documentation has details of different instance types and the corresponding compute details. So when we had to choose an instance type, we did not have any GPU requirements because we're not running any deep learning models. So we tried a couple of CPU instances and chose the one that is best suitable for our requirements. To ensure resiliency, we can host a SageMaker endpoint across multiple instances. We wanted to host our endpoint across 3 availability zones, so we choose the instance count as 3. We define the instance type and instance count in the configuration of the before mentioned workflow lambda, and the SageMaker endpoint config step picks up this configuration and creates the endpoint with this specified values. If we have to update the instance type and the instance count in the future when our requirements change, then it's a one-line config change for us in the workflow lambda. Coming to the inference side of things. As Michael mentioned, SageMaker provides different inference options. Real-time inference. So for our couple of our use cases for like personalized report recommendations and personalized follow recommendations, for which we need like live predictions, we use real-time inference. When a user visits a page with recommendations component on our research portal or app, the request is sent to a ECS service in one of our AWS accounts. Then the request is forwarded to API gateway in a different AWS account, and then the request goes to the SageMaker endpoint, which returns the predictions for that user. ECS service helps us do some checks and ensures that the user is only getting the content that they are entitled to. We also use the batch transform option of SageMaker inference for our related reading use case. Let me go through the architecture. In GIR, reports get published throughout the day. We have a Lambda running every hour to fetch these documents. Once we have a set of documents in the past hour, then we run a batch transform job. This batch transform job uses Universal Sentence Encoder pre-trained model and generates document embeddings for this set of documents from the past hour. Once the document embeddings are generated, then we run a processing job. This processing job creates an embedding matrix with all these documents if we are running it for the first time. If there is already an embedding matrix that is existed, then the processing job appends the newly created document embeddings to the existing embedding matrix. The other event that happens in parallel that you can see at the bottom is users read reports on our website or app. A Lambda fetches this readership every 5 minutes, and then we have a training job running collaborative filtering model which trains on this readership data to create a user similarity matrix. So when a user is reading a document and a request comes in to get related reading recommendations, the SageMaker endpoint combines the document similarity and user similarity to generate related reading recommendations for that particular user and for that particular report. So that's how we're using a combination of batch transform job and real-time inference here. Mainly the batch transform job is useful here because we run it every hour and we have a set of documents to create the embeddings for, and we don't need any real-time embedding generation here. We are also using multi-model endpoints to build an experimentation platform. So after deploying a few models to production, we wanted to expand on and improve upon these models. A/B testing will help us roll out models more quickly and add changes with greater confidence. Hence, we set up a platform for A/B testing. Earlier, Michael showed us how we can split the traffic randomly by percentages across different variants in a multi-model endpoint. We can also specify a variant in the request to the endpoint. But currently, there is no way in SageMaker where we can ensure that a user gets a particular variant throughout the experimentation. So on our experimentation platform, we wanted a user to have sticky variant and get a persistent experience during the experiment. The way we implemented this is whenever a user request comes in, we have the user ID and few other attributes in the request body. The request goes to API Gateway, which invokes a variant Lambda. We use Elasticache, which is AWS resource for Redis cache, to store the user variants for an experiment. So when the request comes to the variant Lambda, it checks if that user already has an assigned variant in the Redis. If the user doesn't have an assigned variant, then we run some statistical methods to assign a particular variant to that user. Once the user has a variant and it's stored in Redis, then the request is forwarded to the user's assigned variant in the SageMaker multi-model endpoint, which returns the results. In the result, we also send back the variant name so that we can track the user engagement with different variants and store all the metrics. So throughout the duration of our experiment, these client engagement metrics are being stored in Snowflake. At the end of the experiment, based on these metrics, we run some statistical tests to decide if our new changes have any significance, and based on it, we decide which is the best variant for us. This is how we're using different SageMaker options for different use cases. Now coming to monitoring side of things. So post-productionizing the ML models, we monitor some metrics using Datadog to ensure that the performance is in line with other components on our website. Datadog is a monitoring service for cloud-scale applications. We currently use Datadog to monitor all other different services. So there is also a Datadog SageMaker integration, which has been very useful to set up the required monitoring. We monitor different metrics like traffic on our SageMaker endpoints, the prediction latencies, and the error rates. We also get alerts whenever there are any anomalies so that we can quickly fix the issues. After deploying the recommendation models using these workflows, we have all our SageMaker endpoints serving low latency predictions, all about 150 milliseconds. We have highly available endpoints with almost zero downtime. This is mainly due to hosting our endpoint in multiple instances across multiple availability zones. Also, if the retraining job fails for some reason in our step function workflow, we still serve predictions as the existing endpoint wouldn't be updated until the training job runs successfully. We also achieved 60% more efficiency in productionizing our ML models. This is mainly due to the fact that based on our architecture and the process that we have built, the deployments are all one click right now, and we don't have to spend half a day checking if the retraining has happened fine and if the endpoint is up and serving the updated predictions. Cost effectiveness has improved as we spend 1/3 the cost now compared to on-premise. This is mainly due to the fact that we need less time and less number of people for maintaining our ML models, and we can spend more time on development. I would like to share a few highlights of our journey. We built a cloud-native end-to-end model-agnostic architecture which is reusable for our future model development. In that process, me and my team learned a lot about MLOps best practices and tried to incorporate them as much as possible. Since this was the first time SageMaker was being set in Goldman Sachs, whenever we hit blockers or needed guidance, AWS team was always helpful and available for us. Last but not the least, we are a team of 4 who deployed our first model into production using SageMaker in 4 months, and now within a year we have about 4 models running in production. This is what we have done until now using SageMaker. We have a lot more planned for our future machine learning pipeline work. We want to leverage other options of SageMaker. Some of the features that we are currently exploring are Model Monitor. In addition to the post-production monitoring that we do using Datadog, we also want to monitor model and data drift during the training processes. And we're also exploring Feature Store to store and reuse the features across the models. Lastly, we're also looking into Clarifai for explainability on our results. Thank you for listening.